Okay, linear algebra, let's try. Any questions about linear maps, which is the topic we are studying? And last week we did section 3b, or null spaces and ranges for a linear map. So let me just review that briefly, and then I will talk about matrices. So a linear map T from a vector space V to a vector space W is a function with the following two properties. T of V1 plus T of V2 is T of V1 plus T of V2 for all vectors V1, V2, and V. And T of C times V is C times T of V for all vectors V in the vector space V and C in the field. So really, we spend the whole rest of the semester studying linear maps. And what is called the null space of T is the set of all vectors in V such that T of V is 0 in W. So we always have this picture. Here's V, here's W. Here's this map T from V to W. Every vector space has a 0 vector. And 0 always gets mapped to 0. But of course, there can be more elements of V that get sent to 0. And the set of everything in V that gets mapped to 0 is what is called the null space of T. And when you map V into W, it's not necessarily the case that every vector in W is the image of some vector in V. And every V goes to some element of W. So what is called the range of V, the range of T, is the set of all vectors, I'll say W in W, such that W is in fact T of V for some V in the vector space V. So sitting over here in W, we have the range of T. So this is the range of T, and this is the null space of T. And what is the superstar theorem about these is the following. If V is finite dimensional, then the dimension of V is the sum of the dimension of the null space of T plus the dimension of the range of T. And this is one of the fundamental theorems in linear algebra. The book calls this the fundamental theorem of linear maps, which is a perfectly good name. And one consequence of this is a very important result about systems of linear equations. So remember in high school algebra, you often solve 2 equations and 2 unknowns, or 3 equations and 3 unknowns. But in general, you have a system of linear equations, A11x1 plus A12x2 up to A1 and xn. And these equations are called homogeneous if the right-hand sides are all 0. So this is the first equation, and you have the second equation. And let's say altogether, you have m equations. So what we have are m equations in n variables. x1 up to xn. And a system of equations that's homogeneous always has the trivial solution. That's when you set all the variables equal to 0. And then, of course, you get 0 equals 0 for every equation. And the question is, when does a non-trivial solution exist? And it's a consequence of the fundamental theorem that if you have more variables than equations, so if n, the number of variables, is strictly bigger than m, the number of equations, then a non-trivial solution, that means a solution where at least one variable is not 0, exists. And let me show you. So for example, let me just to show this is not so completely obvious. Suppose I have 7x plus 2y minus 11z equals 0. 102x minus 13y plus 29z equals 0. 721x plus 1002y minus z equals 0. So here, oops, sorry, let's see if we can get this. Forget that equation. Here I have n equals 3 variables, m equal 2 equations, and 3 is bigger than 2. That means the number of variables is bigger than the number of equations. So there's a non-trivial solution. And so even though you can't just write it down, there is a non-trivial solution. Now, it's not that hard to find, but if you simply want to know if there's a non-trivial solution to this homogeneous system of 2 equations and 3 variables, the theorem I just said proves it. And how does one prove the result? How does one prove this? That if you have a homogeneous system of linear equations with more variables than equations, there must always exist a non-trivial solution. So remember, we have a system of equations. So let's define a linear map from n-dimensional space to m-dimensional space. So define this linear map as follows: T of the vector x1, x2 up to xn. So this has to be a vector with m coordinates. Remember, this was my system of linear equations. So the ith equation in that system was summation j goes from 1 to n, aij x of j equals 0. That was the equation. So let me write just this left-hand side as the first coordinate with I equal 1, summation a1j xj j goes from 1 up to n. Second coordinate would come from the second equation. Summation j goes from 1 up to n, a2j xj, all the way up to the nth coordinate. Summation j goes from 1 up to n, a sub mj xj. So this map is linear. How do you know it's linear? Well, you can just write down two vectors, x1 up to xn and y1 up to yn, and check this. It takes a piece, takes a big piece of paper. You can check it. This is linear. Rn to Rm, what does that mean? It means that by the fundamental theorem, n, which is the dimension of Rn, is the dimension of the null space of T plus the dimension of the range of T. But the range of T sits inside of Rn. So this dimension is at most m. So this is less than or equal to the dimension of the null space of T plus m. To subtract n from both sides, n minus m is less than or equal to the dimension of the null space of T. And n is bigger than m. So n minus m is at least 1. So the null space of T has dimension 1. It means that the null space of T is not just the 0 vector. But what is the null space of T? If a vector is in the null space of T, T of that vector is the 0 vector. That means each of these equations is equal to 0 for that choice of value of the vector x1 up to xn. And there's a non-zero vector x1 up to xn in the null space. There's a non-trivial solution of this system of n homogeneous equations in n variables. So that's a proof. And again, of course, when I go through it, it sounds sort of quick, but there's a lot going on and a lot you have to understand. It takes a lot of time to understand all this. By a lot of time, I mean often hours, not minutes. That's what's involved in learning. So. Any questions about this? Okay. So that brings us to the topic of the day. There are matrices. So a matrix is a rectangular array of numbers. So an m by n matrix is a rectangular array of numbers with m rows and n columns. So for example, a 2 by 2 matrix looks like, well, you often write it A, B, C, D, or if there's only four coordinates, or I would write it as A11, A12, A21, A22. Like 7, 0, minus 3, 1. This is a 2 by 2 matrix. A 3 by 2 matrix has 3 rows and 2 columns. So the first row might be A11, A12, the second row A21, A22, the third row, A31, A32. And the fixed standard notation is Aij is the number or the coordinate in row I, column J, of the matrix. So this is the notation which is used consistently all through mathematics. If you have a matrix with m rows and n columns, the first coordinate in Aij, the I, tells you the row. So I can go from 1 to m. And the second coordinate, j, tells you the column. So that can go from 1 to n. So for example, if A is the matrix 8, 4, 5, minus 3i, this is a matrix with complex numbers as coordinates. So 8, 4, 2 by 3 matrix. The third coordinate in the first row is 5 minus 3i. In the second row is 1, 9, and 7. So this is a 2 by 3 matrix. 2 rows, 3 columns. So in this matrix, the number 7 is in the second row and the third column. So A23, second row, third column is 7. A12, that's the number in the first row, second column. First row, second column is 4. A13, the number in the first row, third column is 5 minus 3i, and so on. Any questions about this? You might have seen 2 by 2 matrices in high school algebra or pre-calculus. If you want to solve the equations ax plus by equals.
Professor.
Yeah.
Yeah, it kind of looked like A23. It didn't look like A23. How much space should be in there?
It doesn't matter, whatever you want. Sometimes, if it's ambiguous, perhaps you can put in a comma.
Will you accept if I do this?
Of course. That's
okay.
Yeah. So if you have ax plus by equals r and cx plus by equals s, there's some formula for x and y in terms of what is called the determinant of the matrix. But you write down the matrix. So this has a, what they teach you in high school algebra or pre-calc is that this system of equations has a unique solution if AB minus BC is not 0 and X is connected to the matrix RSBD over ABCD, and Y is connected to the matrix ACRS over ABCD. But it's actually the determinant of these things. But if you haven't seen this before, ignore it. But if you have seen it before, it's just to point out how matrices come up already in pre-calculus when you're trying. It's one way to solve 2 linear equations in 2 variables. So there is a fundamental connection between a linear map and a matrix. So suppose T is in L of VW. Remember, L of VW, this is the vector space of linear maps T from V to W. So T is a linear map. And suppose V and W are finite dimensional vector spaces. So let the dimension of the vector space V be n, and let V1, V2 up to Vn, this list of vectors, be a basis for V. So I specified a concrete basis for V. Every vector space has infinitely many different bases, but you fix one basis. Suppose the dimension of W is M. And we let W1 up to W2 up to Wn. Be a basis for W. So the matrix, so every linear map from a finite dimensional vector space to another has a basis. Has a matrix. The matrix for T is going to be an m by n matrix, m of T, and Aij. For some reason, I hate that the book is using AJK. That doesn't matter. These are the coordinates of this matrix, an m by n matrix. So there are m rows. So J goes from 1 up to m, and K goes from 1 up to n. So I want to define a matrix from this linear map. And we do it in the following way. So here is the formal definition. Then I need to write down some examples. So T is this linear map from V to W. So this has a basis V1 up to Vn. W has a basis W1 up to Wn. So if I take any vector Vj in the basis, T of Vj is a vector in W. That means T of Vj is a linear combination of the vectors in the basis for W. So I can write this as summation. K goes from 1 up to m, A sub jk, W sub k. This is W1 up to Wm. So because this is a basis for W, every vector in W has a unique representation as a linear combination of the vectors in the basis. So if each of the basis vectors of V, V sub j, is some linear combination. And from this, I get the matrix M of T, which is A, JK, which means what? So T of V1 is summation A1K WK, K goes from 1 up to M. I write these coordinates as the first column of my matrix. A11, A21, T of Vj is let me do this again. I don't like the way that, I don't like the notation the book is using, but I have to stick with the notation. So again, V has a basis V1 up to Vn. W has a basis W1 up to Wn. And I have this map T, a linear map from V to W. So T of the vector Vk is going to be summation Ajk W sub j, j goes from 1 up to n. So for every k between 1 and n, because the vk's are the elements of the basis for v, t of vk and w is a linear combination of the wj's, and I write the coordinates like this. And m of t is the matrix for t. This is going to be an m by n matrix. So if I look at t of v1, I take those coordinates and I use those as the first column of my vector. This is a11, a21 down to am1. If I take t of v2 and I look at these coordinates, these will form the second column of my vector. a12, a22 down to am2. All the way up to the nth vector, vn, when k is equal to n, the coordinates are a1n, a2n, down to amn. And this is what is called the matrix of my linear transformation. And I'll explain in a minute why this is so important, but let me just calculate an example. So this is the first example in the text. This is in section 333. We have a map T, a linear map from a two-dimensional space to a three-dimensional space, defined by T of the vector xy is x plus 3y, 2x plus 5y, 7x plus 9y. So again, you have to check or have already proved in general that a linear map of a map of this form is a linear map. So what is the standard basis for F2? It's the vector 1, 0, and 0, 1. And the standard basis for F3 are the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So what does T apply to these basis vectors? What is T of 1, 0? T of 1, 0, when x is 1 and y is 0, you get 1, 2, 7, which is 1 times 1, 0, 0, plus 2 times 0, 1, 0, plus 3 times 0, plus 7 times 0, 0, 1. And T of 0, 1, when x is 0 and y is 1, I get 3, 5, 9, which is 3 times 1, 0, 0, plus 5 times 0, 1, 0, plus 9 times 0, 0, 1. So the coordinates for T of 1, 0 are 1, 2, 7. So in the matrix for this linear transformation, the first column is 1, 2, 7. And T of 0, 1 is this linear combination of the basis vectors for W. W is F3. The coordinates are 3, 5, 9. So this is the matrix for this linear map. Any questions about this? Okay. What about another example? So remember, the polynomials form a vector space. Polynomials of degree bounded above by some number form a subspace. So in particular, P3 of R is the set of all polynomials of degree at most 3. And every such polynomial is a linear combination of the polynomials 1x, x squared, and x cubed. And these 3 polynomials are the standard basis for P3 of R. For P2 of R, these are polynomials of degree at most 2. And every polynomial, every quadratic, or every polynomial that's at most quadratic is a linear combination of 1x and x squared. So the dimension of P3 of R is 4. These 4 vectors form a basis. The dimension of P2 of R is 3. These 3 polynomials form a basis. And suppose we take D, the linear map from P3 of R to P2 of R be differentiation. But we already showed, actually learned in calculus, that differentiation is a linear map. And the derivative of a polynomial is a polynomial of 1 less degree. If you have a polynomial of degree at most 3, the derivative is a polynomial of degree at most 2. So differentiation maps this vector space to this vector space. And what is the matrix for this linear transformation? So derivative of the constant function 1 is 0. So in terms of a linear combination of 1x and x squared, this is 0 times 1 plus 0 times x plus 0 times x squared. So this is going to be the derivative, the matrix for differentiation. You're going from a 4-dimensional space to a 3-dimensional space. This will be a 3x4 matrix. And the first column is 0, 0, 0. The derivative of x is 1, which is 1 times 1 plus 0 times x plus 0 times x squared. So the second column has coordinates 1, 0, 0. The derivative of x squared is 2x, which is 0 times 1 plus 2 times x plus 0 times x squared. So the second column is 0, 2, 0. The derivative of x cubed is 3x squared, which is 0 times 1, 0 times x, 3 times x squared. So the fourth column has coordinates 0, 0, 3. So this is the matrix for the differentiation operator. Now, matrices themselves are very important, significant algebraic objects, and we can perform certain algebraic operations on them. For example, we can add matrices, but we can only add matrices when they are matrices of exactly the same size. So suppose we can add two m by n matrices. So suppose I have the matrix A11, A1, AM1, A12 down to AM2, A1n down to AMn. This is one m by n matrix. And I take another matrix of exactly the same shape, say B11, BM1, B12 down to BM2, B1n down to B. And you add just by adding the coordinates in the same location. So when I add this matrix to this matrix, the entry in the first row, first column, you take the entries in the first row and first columns of the two matrices and you add them together. And you do this all through at every location in the matrix. So in row M, column 1, it's AM1 plus BM1. All the way across. And you finally get to the end, it's A1n plus B1n down to ANN plus BN. So for example, if you have the matrix 270 minus 152, and the matrix 39 minus 4, 117, and you want to add them, you add the coordinates in the same locations. 2 plus 3 is 5, minus 1 plus 1 is 0. 7 and 9 is 16. 5 and 1 is 6. 0 minus 4 is minus 4. 2 and 7 is 9. So this is the operation of matrix addition. And this works very nicely because if we have linear maps S and T from V to W, then S plus T is also a linear map from V to W. And the matrix of S plus T is the sum of the matrices of S and of T. Of course, you only can talk about the matrix of a linear map once you've fixed bases for the vector spaces V and W. And when we write this, we mean we fixed bases for V and W, and we're computing ST and S plus T with respect to those bases. There's also scalar multiplication of a matrix. Namely, if you take a scalar lambda and a matrix when you multiply the matrix by a scalar, you multiply every coordinate by the scalar. So this is lambda A11 down to lambda A M1. This is lambda A1n down to lambda A. So for example, you take the matrix 2793, and multiply it by 4, you get 4 times 2, 4 times 9, 4 sevens, 4 3. And again, if T is a linear map from V to W, and lambda is a scalar, then the matrix of the linear map lambda T is lambda times the matrix of T. Any questions about this? And FMN is the set of all m by n matrices. This always means m rows, n columns, all m by n matrices with coordinates, the entries of the matrix. And with the operations of vector of matrix addition and scalar multiplication of matrices, we can check that this is a vector space of dimension m times n. So if you have an m by n matrix, you have n rows, each with m coordinates, they're mn coordinates, and that is exactly the dimension of this vector space. All right, now we can add matrices, and it's a natural question to ask if you can multiply them. So, or maybe there are many different ways you could define a multiplication where you want to figure out the correct multiplication. If you have two, let's say 2 by 3 matrices, 1, 2, 3, 4, 5, 6, and B is another 2 by 2 matrix, 7, 8, 9, 10, 11, and 12. We want to know, can we multiply AB? How do you multiply this by this? And the answer is not possible. In a way that is consistent with what we want to understand. So, and what I mean by, in a way, we want everything to work properly. Suppose we have a linear map T from a vector space U to V. So we have 2 maps, and another linear map S from a vector space V to W. So we have U goes to V with this map T, goes to W with a linear map S, and then we have the composite map S composed with T. And let's say that the dimension of V is equal to N, dimension of W is equal to M, and the dimension of U is equal to P. So the matrix for T, if T is a map from U to V, U so U is dimension P, T is from U to V, S is V to W, W has dimension M. So the matrix for T is going to be an N by P matrix. The matrix for S goes from V to W. W has the dimension M and V has dimension M. So the matrix for S is going to be an M by N matrix. And ST goes from U to W, from U to W, U to W. So the matrix for ST is going to be an M by P matrix. And we would hope that the matrix for ST is the product of the matrix for S times the matrix for T. Now this is an M by P matrix. This is an M by N matrix. This is an N by P matrix. So in order for something like this relationship to hold, you have to be able to multiply matrices of two different shapes, but where the number of columns of the matrix on the left equals the number of rows on the matrix on the right. So in order to have the possibility of matrix multiplication being consistent with composition of linear maps, we need to define a multiplication of two matrices where the number of columns of the matrix on the left equals the number of rows of the matrix on the right. So that's our goal. And there is a way to do that, which is a little bit complicated when you're learning it, but then becomes just second nature. It's the following. So what was it that I wanted to multiply? Matrices M by N and N by P. So my M by N matrix, and it has to be consistent with it. So I want S to be my M by N matrix. Remember, S is a linear map in my picture from V to W. And V had dimension M, N, and W had dimension M. So the matrix for S was an M by N matrix, and T was a linear map from U to V. The dimension of U was P, and the dimension of V is still M. So M of T is a M by P matrix. So suppose M of S is the matrix A sub and M of T is the matrix CJK. So let me just kind of draw a picture of this. So A11 down to A1, AM1, A1, N down to AN. This is the matrix S. And the matrix T has M rows, all the elements C, C11 down to CN1, N rows, and P columns. And I want, so this is N by N, this is N by P, and I want to multiply them and get a matrix ST, which has M by P dimension. And so the rule is, how do I get the element in row J column K of this product matrix? And the answer is, I take the jth row of the matrix A. The jth row goes AJ1, AJ2, up to AJN. And I take the kth column of the matrix T, C1K, C2K, down to CNK, and I multiply the row into the column. What that means is I take the first element times the first element, AJ1, C1K, second element times the second element, AJ2, C2K, all the way down till I get to the product of the last element of this row times the last element of this column, AJN, CNK. Or in sigma notation, that's summation, AJR, CRK, R goes from 1 up to N. And that somewhat complicated formula is the formula for matrix multiplication. So the condensed formula is the following. If you have this matrix A and the matrix C, the jkth coordinate of the product matrix AC is summation AJR CRK, R goes from 1 up to N. So let me look at a couple of simple examples. Those I have 1, 2, 3, 4 times 5, 6, 7, 8. How do I multiply these two matrices? It's row into column. So the entry, this is 2 by 2, and this is 2 by 2, and the product is going to be 2 by 2. And the first entry, the coordinate in the first row, first column, I take the first row times the first column. That's 1 times 5 plus 2 times 7. This is first row, second column. Multiply the first row into the second column. 1 times 6 plus 2 times 8. This is second row, first column. I take the second row into the first column. 3 times 5 plus 4 times 7. This is the second row, second column. Multiply the second row into the second column. 3 times 6 plus 4 times 8. So this matrix is what? 5 plus 14, that's 19. 6 plus 16, 22. 15 and 28, which I think is 43. And 32 and 18, which is possibly 50. So the product of these two matrices is this. So hopefully I did the calculation right. I'm never sure, but hopefully I did it right. And you need to make sure you understand this. And as a simple test, Here's a little problem. Just calculate these matrices: 3 minus 1, 0, 5, and 2 minus 1, 3, 8. So here's a 2 by 2 matrix and a 2 by 2 matrix. Multiply them together and tell me what you get. I think we got an answer. It's going to be another 2 by 2 matrix. What's the coordinate in the first row, first column? You multiply this row into this column, you get 3 times 2 is 6, minus 3 is 3. For the first row, second column, you multiply this row into this column, you get minus 3 minus 8, minus 11. This is the second row, first column. So the second row into the first column is 0 plus 15. And second row, second column, multiply the second row into the second column, you get 0 plus 40. So that's the answer. Let's do one more example. We'll do more than one more example. Here's a matrix: 1, 2, 3, 4, 5, 6. This has 3 rows and 2 columns. And here's a matrix: 6, 5, 4, 3, 2, 1, 0, minus 1. This has 2 rows and 4 columns. So the number of columns in the matrix on the left equals the number of rows in the matrix on the right. So you can multiply them. And the result will be a 3 by 4 matrix. It's like these 2's cancel, you have a 3 by 4. So it's 3 rows, 4 columns. So what's in the first row, first column? This row into this row is 6 plus 4 is 10. First row into the second column, 5 plus 2 is 7. First row into the third column is 4 plus 0 is 4. First row into the fourth column is 3 minus 2 is 1. What about this row? Second row, first column, 18 and 8 is 26. 15 and 4 is 19. 12 and 0 is 12. And 9 minus 4 is 5. And for the third row, first column, I get 30 plus 12 is 42. 25 and 6 is 31. 20 and 0 is 20. 15 minus 6 is 9. If I did my arithmetic correctly, this 3 by 2 matrix times this 2 by 4 matrix is this 3 by 4 matrix. Okay? And with this definition of matrix multiplication, it is in fact the case that the matrix for the product of two linear maps is the product of the matrices of the linear maps. The matrix of the product is the product of the matrices. So there's one very, very nice way to look at matrix multiplication. Suppose we have a matrix with just one row this is a 1 by n matrix, and another matrix with one column. So this is n rows and one column. So when I have a 1 by n times an n by 1, that's going to be 1 by 1. That means a number. In fact, when you multiply this matrix into this matrix, which is this row vector into this column vector, you get A11 C11 plus A12 C21 up to A1n Cn1. This is just a number or a 1 by 1 matrix. So if you have 7, 2 minus 3 multiplied into 5 minus 4, 1, this is 35 minus 8 minus 3, which is 24. Any questions about this? This is really just a lot of almost high school algebra, because there's no vector spaces here or anything sophisticated. It's just playing with matrices. So let's look at another example. Here's an example I worked out a moment ago. Let me look at this for again. 1, 2, 3, 4, 5, 6. And 6, 5, 4, 3, 2, 1, 0 minus 1. That was 10, 7, 4, 1, 26, 19, 12, 5, 42, 31, 29. Example, the number 19 is in the second row, second column. I take the second row times the second column, I get exactly 15 plus 4 equals 19. But every element of the product matrix, the element in the jkth coordinate position, is row j of the first matrix times column k of the second. And how do we get this whole column? This whole column, so this is first row, second column multiplied, second row, second column, third row, second column. If I take my matrix 1, 2, 3, 4, 5, 6, and multiply it by the second column, 5, 1. So this is 3 by 2. This is 2 by 1. So the product will be 3 by 1. That is, this is 7 plus 2, 5 plus 2 is 7. 15 plus 4 is 19. 30 plus 6, 25 plus 6 is 31. That's exactly my second column. So in general, if you have a matrix A times a matrix C, and so this is, again, n by n by p, and AC is m by p. If you want the kth column of the product matrix, it's A times the kth column of C. I want to keep looking at these examples because we have 1, 2, 3, 4, 5, 6. This matrix times the column vector 5, 1. And we saw we got 7, 19, 31. But this is really the same as 5 times the first column plus 1 times the second column. Because 5 times the first column is 5, 15, 25 plus 2, 4, 6. That's exactly this. And if we put this together, this is, again, these are all just calculations. If you have an m by n matrix A, and you have a column vector C, it's an n by 1 matrix, or a column vector. The matrix A times the matrix C is, you take the first column of A, times this coordinate C1, the second column of A, times C2, up to the last column of A, times this coordinate C1. So when you multiply a matrix times a vector times a column vector, you get this linear combination of the columns of the matrix. Any questions so far? Let me just do a few examples and then we'll be done for the day. Let's take a matrix. So this is a 3 by 4 matrix. Let me multiply it by this column vector, 2 minus 1, 4, 2. So this is a 4 by 1 matrix. And the result will be a 3-dimensional column vector, 3 by 1. And I claim this is exactly what you get by taking the first column of this matrix and multiplying it by 2, which is scalar multiplication of a vector by a number, minus 1 times the second column, plus 4 times the third column, plus 2 times the fourth column. This is 6, 4, 10, minus 8, 0, 2, plus 4 times this, 4 minus 16, 28. 2 times this is 0, 2, 18. So 6 minus 8 is minus 2, plus 4 is 2. 4 minus 16 is minus 12, plus 2 minus 10. 10 minus 2 is 8, plus 28 is 36, plus 18 is 54. If this is correct, multiplying this matrix by this column vector, it's this linear combination of the columns in my matrix. And when you do the arithmetic, this is what you get. And if we just did matrix multiplication, row into column, what will we get? We will get 6 minus 8 is minus 2, plus 4 is 2. 4 minus 16 is minus 12, plus 2 is minus 10. 10 minus 2 is 8, plus 28 is 36, plus 18 is 54. So it all works out nicely. So that's what this section is about, matrices and the arithmetic in matrices. So I've actually prepared some lecture notes written out, which also cover this material with more examples, and I will post them later today on Blackboard and email them to you. But we'll have a review for the midterm exam on Wednesday, and the exam itself will be a week from today, next Monday. So we have 2 midterms and a final, and that's the story.
Professor.
Yes, sir.
So when it comes to the formulas, are we required to keep them in our heads, like memorize them, or
No, it'll be an open book test.
Okay, thank you.
I mean, when it's done on Zoom, it has to be open book. Any other questions for today? Okay. Stay well. It's a complicated time in the world. If you follow the news, stay well. Be back on Wednesday. Bye all.